So here in this question, we have to find the minimum value for Vi to saturate. It's given that V1 is greater than V2. That means positive is greater than negative. Our input is going to be positive because we know that Vi is equal V plus minus V minus. So Vi is equal, instead of V plus, that is V1 minus V2. And it is given V1 is greater than V2, Vi is greater than 0. So from this graph, if Vi is greater than 0, it might be somewhere over here. Okay, because this region is very small, around 150. Now we will get that. So what we are going to do is we are trying to get what is this value. What is this value? For what value it gets saturated? So this voltage Vin is positive. So for this positive, we get positive saturation plus VCC. If it was negative, then we get the negative saturation. So here, V input is positive. Therefore saturates, and when saturated, V out is equal plus VCC. So we know during amplification, we had an equation V naught is equal A times V in. So V naught is going to be plus 15 and A is 10 to the power 5 into Vi. So Vi is equal 150 microvolt. So for this small voltage, for this small potential difference between the two terminals, it gets saturated. Got it? So we can mention that Vi required to saturate is very small, Vi required to saturate is very small. Now, due to this fact, for a very small voltage, it gets saturated. Can I use the open loop configuration as an amplifier? Will it be suitable? Is this suitable for amplification, the open loop? It is not. Okay, we cannot use this one as an amplifier, but still this one has a good application. That is, you can compare the voltage. For example, now let's say, don't note this, don't draw what I'm drawing now. Now let's say we have two voltages, V1 and V2, and this is plus 15. Negative supply is minus 15. Let's say that V1 is greater than V2. This is the positive terminal. And this is the negative terminal. What can you tell about Vi? Vi is greater than 0. If Vi is greater than 0, then the output will be plus 15. Okay. And let's say that V2 is greater than V1. Let's say V2 is greater than V1. If V2 is greater than V1, what can you tell about Vi? Vi will be less than 0. Why is that? Always remember, Vi means V plus minus V minus. So you get Vi less than 0. When Vi is less than 0, in which side will it saturate? Plus 15 or minus 15? It goes to minus 15. Okay, is that point clear? Give me a minute. Okay, so we can use this one as a voltage comparator. Next topic, voltage comparator. So we can make a flame sensor using a voltage comparator. A flame sensor. So we have two LEDs. Here this is a resistor R1, R2, R3, and this is going to be a diode. Uh, Sorry, this is an LDR. LDR. So LDR is a light dependent resistor. Light dependent resistor. This, let's say, is the positive terminal, and this is the negative terminal of this op amp. And we have plus VCC and minus VCC. Minus VCC. This is our supply plus VCC. Let's say plus supply, plus V supply, voltage supply. Now here, um, here we have a candle. We have a candle. So when this candle is lighting, the light falls on the LDR. So the resistance of the LDR goes down. So if there is light, LDR resistance is less. So let's say this is voltage V1 and this is voltage V2. If this is less, if the resistance of the resistance is less, then V1 will be less than V2. V1 less than V2. So if V1 is less than V2, what can you tell about the output? Output will be negatively saturated because Vi is less than 0. Therefore, it is negatively saturated. This side is negative, and we have earth. We have grounded this side. So, in which direction will the current flow? The current, let's say this is the green LED. This is a green LED. And this is a red LED. This is a red LED. Which one will light up? This is 0 volt, this is minus. Therefore, current can move or current can flow in the upward direction. But it cannot come down because this is negative. The current will try to go in this direction, but when it is reverse biased, the diode won't work. This is forward bias. Therefore, this LED will work. So here, when the light is on, we get green LED lighting up. Let's see when the light is off. When the light is off, resistance goes up. LDR resistance increase. If this resistance increase, V1 will become greater than V2. V1 greater than V2. Then Vi is greater than 0. If Vi is greater than 0, output is positively saturated. If this is positive, the current will try to flow down. Therefore, the green color LED becomes reverse biased and the red color LED becomes forward biased. Therefore, the red color light lights up. So, by comparing the voltage, by comparing this single voltage, by comparing V1 with fixed V2, we can make a flame sensor. We can just check if the flame is on or off. Is the idea clear? How we can use this operational amplifier as a voltage comparator? Draw this diagram. if the candle is lit, LDR resistance decrease. V1 decrease. V1 is less than V2. Therefore, Vi is less than 0. Vout is equal minus VCC. So if this is minus VCC, candle is lit, right? If this is minus, green is forward bias, red is reverse bias. Red LED doesn't work. Green LED does work. And the opposite is if candle is off. If the candle goes off, then LDR resistance increase, V1 increase, that is V1 is greater than V2. Therefore, Vi is greater than 0 and V0 is equal plus VCC. Now, red color works, but red works, green goes off. Green goes off. When you're done, let me know. When you have copied, let me know. Now, note, did you observe something? The plus VCC and minus VCC, we have the positive and the negative value, the same values. So how do we actually obtain that? It is like this. We connect now I want to provide a supply of plus 10 and minus 10. I want to provide a supply of plus 10 and minus 10. Then what I do is I connect it to a battery. I connect it to a battery of 20 volt. And the center, The center, we ground it. We ground the center and provide the negative supply to the negative terminal. Now, if these two together is 10 volt and these two together is 10 volt, this will be positive 10 and this terminal would be at negative 10. So that is how we provide plus VCC and minus VCC. Note it down. And we usually generally supply a balance. If this is 10, this is minus 10. If this is 15, this is minus 15. Okay, we don't give asymmetric values. We keep it symmetric. Next topic, operational amplifier. Operational amplifier in closed loop, and negative feedback and negative feedback. So we know what is a feedback and we know what is closed loop. If we give a feedback, it is closed loop. Then we know what is feedback, but what is negative feedback? We have two terminals. We have a positive terminal and a negative terminal. If we provide the feedback to the negative terminal using a feedback resistor, then we call it as negative feedback. Then in case we provided a feedback like this, then how would we call this feedback? How do we call this feedback on top? It will be positive feedback because we give the output back into the input of the positive terminal. Okay. So here it's negative feedback. Therefore, using that resistor, we will have to give the output back to the input of the negative terminal. When a fraction of the output, when a fraction of the output voltage is supplied, back into the input, it is known as feedback. It is known as feedback. And the resistor used here, is the feedback resistor. Feedback resistor RF. the operational amplifier, in the closed loop, and negative feedback in the closed loop configuration and negative feedback and negative feedback and negative feedback can be used as an amplifier, can be used as an amplifier. Under the above condition, the op amp follows the golden rules. Follows the golden rules. What are the golden rules? So golden rules mean if the op amp is in closed loop and negative feedback, we have two special rules. So those two special rules, we call them as the golden rule. Golden rule 1. Golden rule 1. The first golden rule is when an op amp operates in linear mode, when an op amp works in linear mode, the voltage difference between the voltage difference between the inverting and non-inverting, inverting and non-inverting. So inverting means that's the negative terminal and non-inverting means the positive terminal. Terminals is zero. Golden rule 2. The current flowing through the op amp, the current flowing through the op amp the current flowing into the op amp through the input terminals is zero. So if I show these two in a diagram, these two rules in a diagram, This is my block diagram. Non-inverting terminal, inverting terminal. The potential difference between these two, delta V is equal to 0. Rule number 1. And the current entering into the terminal entering into is 0. Let's say I is equal to 0. So those two are the golden rules. Remember, it is only applicable for closed loop. Oh, we forgot to make it a closed loop. Closed loop and negative feedback. Otherwise, it is not valid. So during this situation, when it is working as an amplifier, it will remain in this region. It always stays within the linear region. Now we know this is the linear region. Here only it can act as an amplifier, linear region, and this is saturation. Saturation. This is V0 and this is Vi. So far, is it clear? Sometimes you might have not got the idea of what is these golden rules. For now, just have the idea that for golden rules, there is no potential difference and there is no current through the terminals. Other than that, we can discuss that in detail when we do a question or when we do an example. Have you noted up to this? So the amplifier, we can make an amplifier using this operational amplifier. Using the operational amplifier, we can make an amplifier. There we have two types of amplifier. One is inverting amplifier. Inverting amplifier. In an inverting amplifier, now which terminal do we call as the inverting terminal? The positive or the negative? Which terminal do we call as the inverting terminal? We call the negative as the inverting terminal. So in inverting amplifier, we provide the input to the negative terminal. Okay, we provide the input to the negative terminal. Now it is in the negative feedback. Therefore, the feedback resistor is also connected to the negative terminal. Feedback resistor is also connected to the negative terminal. And the positive terminal, let's say it is ground. The positive terminal is ground. Now, we provide an input plus V1. We provide an input V1. So the potential difference between these 2 points is V1. And So here the input, we give an input V1 plus V1. So the input between these two terminals is going to be V1. Let's say this resistor is Ri, the input resistor. So can I apply the golden rules here? Can I apply the golden rules here? To apply the golden rules, what are the conditions? It has to be in negative feedback and it has to be closed loop. Are the both conditions satisfied? Yes, it is in negative feedback. So it is closed loop. Therefore, both the conditions are satisfied. Then we can apply the golden rules. So the golden rule 1 says there is no potential difference between the terminals, between the two inverting terminals. Or they say it's negligible. So what is the potential of positive terminal or the non-inverting terminal? That's 0 volt. Then the inverting terminal, it also has to be 0 volt. Do you get that idea? And the second rule says there is no current entering into the operational amplifier through the inputs. So if this is I, here at this junction, there won't be any current going into. Hence, we can consider that entire current will go through the feedback resistor. And what is this voltage over here? That's V0. Is it clear how I marked these voltage, how I marked these voltages, and how I marked this current? Are those two clear? Okay, now to find out the amplification, I have to get an relationship between V0 and Vin. This is Vin, V0 and Vin. So, using this current relationship, I must be able to get an equation. What I'm going to do is I'm going to apply Ohm's law between these 2 points. So if I apply Ohm's law between these 2 points, that is going to be Vi minus 0 is equal I into R1. That's my first equation. And if I apply from here to here, 0 is greater than V0.